Okay, good morning. Okay, when's our test?
Thursday.
This coming Thursday. At 9:20 here. I'll be here earlier if you wanted to start. So let's say you want to start at 9 o'clock or something like that. That's perfectly fine. If you need to go long, I'll also let you go long. It's going to be the same rules as with the regular class. Okay. So I want to finish up a problem today, and then what I'm going to do is today and tomorrow I'll open it up to questions. Yes.
Did you just say 9:30?
No, on Thursday I'll be here at 9 o'clock. So if you wanted to start at 9, that's fine. If not, it will just be the regular 10-20 class. Okay. Yeah, that's fine. Yeah, that's fine. I mean, if you can't, you can. That's, you know. If you need to go a little bit later, that's fine too. Okay, so we're doing Halley's Comet. And here's the sun. This is the top view. Here's the sun, and it's going to make this elliptical orbit like this. And we're looking at the comet here, and the comet here. Okay, what was the fancy name for this? Well, that's the perihelion. Just means the closest approach to the sun. This over here is called your aphelion, meaning the furthest away point from the sun. Okay. We said that from here to there is, I'll call that RP for the distance for the aphelion. This is the velocity for the aphelion. And then over here, the distance from here to there, this is the distance of the aphelion. This is the velocity of the aphelion. And we said given, basically we wanted to find the velocity here, if you're given. Okay, VP, RP, and RA. Okay, and I think we left by saying this is the conservation of angular momentum problem. Okay, so what I can say is L initial equals L final. Now, why can you say this? When is angular momentum conserved? No external torque. So the reason you can say this is because the external torque equals 0. Why is there no external torque? Okay, so first of all, how do you always calculate torque?
RP, or the cross
No. R cross F. Okay, now what was R cross P? It is something, it's just not torque.
Is it an angular?
That's angular momentum out. We're going to need that in a moment. Okay. So why did we say there's no torque here? We said that this equals 0. Why? So here's the sun. Here's the comet. Convince me there's no torque.
The only thing acting on it is the sun, but the force is going the same as the radius, so it's 0.
Yeah, so this will be the pivot. So from here to there, this is R. Remember, the moment arm always goes from your pivot to where your object is. Now, how's the force of gravity always look? It's directed along the line connecting the two. So the force of gravity is like this. And this is the force that the sun exerts on the comet. Okay, so if you have two things that are anti-parallel, what's the torque? This would be 0. So the torque here, the torque of the sun on the comet, 0. Therefore, you can say that L initial equals L final. Does that make sense? Yes. Right now. Okay, so what is R cross P used for? That's the angular momentum for a point mass. Okay, compared to the sun, what can we view Halley's Comet as being? A point mass. So we can do R cross P for the comet. So I'm going to say L for the comet. It's going to be R cross P. So we're going to calculate it here. And we're going to calculate it here. Okay. So let's do this. So first of all, for right here, how does the L, yes,
So we're using R cross T because of tort, right?
yep,
What about R cross A?
this is torque, it's a different object. Okay, R cross F is going to be the torque for a remote force. Okay. So, what's the direction of the torque at this spot? Up, down, right, left, in, out? Everyone agree? Let's do it. This is R cross P. Why does P go down?
Because that's where it's moving.
The velocity is going down, so then the momentum has to go down. R cross P, thumb's coming out. So, how high does this better go over here? The L over here, it better go out as well, does it?
Yeah.
R cross P is coming out. So let's go look at the magnitude of this guy. So this is going to be magnitude of R, magnitude of P times the sine of the angle between the two. In this case, it's going to be 90. So if you look, I'll put a theta in here. Okay. So over here, the angle here, the theta, this is 90 degrees. What about when I'm over here? What about the angle? This is also 90. Okay. The sine of 90 is 1. So let's just set this up. Okay, so I'm going to say L initial is going to equal L final. So this is going to be what? This is going to be R at the perihelion times the velocity at the perihelion times the sine of 90. Times the mass of the comet times the velocity of the perihelion. This is P of the comet. Okay. Times the sine of 90. Equals, and we do the same thing at the aphelion. So this is R sub A, M sub C, V sub A, sine of 90. Does it matter what the comet's mass is? Cancel. This, sine of 90 is 1. So what are you left with? You're left with RP, VP equals RAVA. So now we just solve for the VA here. So the VA is RP, VP over RA. Is that going to be faster or slower? Is it moving faster here or is it moving faster here?
I feel like it'd be faster, but that might be
Here
wrong.
or here? Here? Everyone agree?
Both there.
Everyone agree? Now you're telling me what's slower.
Because your R is bigger there, so if they're equal, then your velocity has to be smaller.
Exactly. Makes sense? The angular momentum has to be the same. So if you have a really, really small R, you have to have a bigger P. Over here, you have a really, really big R, so you have to have a smaller V. So if you're watching this comet, what would it do? It would do something like faster, 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 slow, 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 faster, 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 faster. It doesn't move at a uniform rate. Okay? That's why when a comet's in the area, first of all, what's a comet? It's kind of a neat thing. It's basically a dirty snowball in space. Okay? There's basically, when the universe formed, there would be these big ice chunks that are dirty, they have a lot of crap in them. Turns out the crap is really important. But it's big, it's basically a big dirty snowball. Okay, so what happens is when the snowball gets close to the sun, it actually starts to melt a little bit, and that's why you get the tail. It's actually losing mass. And then eventually it goes away, and then it starts to freeze. You don't see the tail as much because it's not close to the sun. Okay? That's not cool.
Does it ever lose mass or does it?
Yes, it loses mass all the time. So some comets will eventually die. Okay. We have two types. This is a little interesting piece of history for nature. Okay, we have two types of comets. What kind? We have the kind that basically take about 100 years to go around, that order. Okay, they're called, basically, where do they come from? They come from out past Neptune. So if you go out past Neptune, you have a whole bunch of pieces of big pieces of ice. They're on the plane of the solar system. You call those trans-Neptunian objects, okay? They're not all comets, but some are. Pluto's in a case of a trans-Neptunian object. Okay? So you have those comets that basically come from a little bit past Pluto, and they go like this. So let's say here's the planet of the universe. So here's the sun and all the planets go around them. So here's basically Neptune going like this. If you look past Neptune, you can have some comets out here. So you have comets like this. But you also have comets coming basically from that are on the planet of the universe, the solar system. They come from out here and go like this. They have periods on there of like thousands of years, or tens of thousands of years. And they can come from all directions. And that's why it's speculated that if you go out really, really far from our solar system, you basically have this cloud of things. It's called the Oort cloud. And it's basically it's comets here that have a really, really long period. So the comets that aren't contained in the plane of the atmosphere, plane of the solar system are from the Oort cloud. Probably the most distant part of our solar system. Okay.
Is that why Pluto got bounced from the planet club? Because
Is a trans-Neptunian. So Pluto is what's called a TNO. And a trans-Neptunian. How does Neptunian? And object. So Pluto is just one of the is a large trans-Neptunian object. If you want to call it a planet, that's fine. I don't care.
Why does something become a planet?
That's a great question. Okay, so that's not at all obvious what it is. So first of all, it has to be round. Most people would say a planet must be round. It has to be big enough that basically gravity is pulled enough and on that it's round. Okay, so you'd have to say it's round. You'd also say that it's forming the initial part of the solar system. So everything else was forming, it was forming in that initial stage. And these objects here appear to be basically remnants or basically formed later on. Or that's the argument for it. Okay, but that's actually what a planet is in the eye of the beholder. That's actually an open question. Most people would say this guy here. Okay, who basically led the charge to do this to Neptune? Damn him. Neil deGrasse Tyson. That's actually what he's really famous for. He's the one who basically said, well, Pluto's not really a planet, it's really this stuff. Okay? Interesting thing. Okay, I was going to go into some new topics for the final, but I decided basically to be nice and not do that. So, or actually, I just introduced a new topic 5 minutes before class tomorrow. I'm kidding. Okay, so little joke, little final joke. So what I'm going to do is open up today's class for the rest of the class, and tomorrow's class for the rest of the class for questions. Okay, are you just waving? Okay, you have a question. Yes.
Remember that question yesterday with the wheel, the thing falling off the bed?
Yep.
Can you do another one of those? please?
Sure. Okay.
All these things you asked us.
Yep.
What is the units for the angular?
Angular momentum?
Yeah,
What are units for angular momentum? They're weird units.
because I had to Google yesterday for the homework because I didn't have it in my notes.
The units are a joule second. They're a joule second.
Okay.
So you had a question like this, Peter, where you have here like this, like that. Okay, and find A and T. Okay. This is M. We use R. This is little m. Perfectly fair thing to do on the test. Okay, open it up to you, my people. So far, that's true.
oh, wait, this was like on the homework yesterday.
Yes, it was.
Do you draw everybody that?
Yes, draw for, now what would be the indication here to do it for writing down?
Because it's always right.
It's almost never wrong, so it's never going to usually hurt to have one. Well, here there's something that smells that just screams out free body diagram.
Have tension.
Tension is the force, so if you're asking for a force, you better get a free body diagram someplace. And let's say I didn't ask for the force. If you're still doing an acceleration, you better get a free body diagram. Okay? So, how many free body diagrams will there be?
It's gonna be 2.
2. Here's the wheel. And here's the block. Okay, proceed. Let's start with the block first. What are all the forces on our block? Going up. Right, going down. Where's the normal force? How come? It's not on a surface, so it can't be a normal force. Okay. What would be the coordinate system for this? Yes, just we're going to assume that this is falling. Right, I'm going to assume that this is going down. So is this going to be a standard coordinate here like this? Which way is positive? Down. What about our friend the wheel? Going? Yeah.
It's going
Oh,
down
Down where? Now, where you put it matters.
on the side of that thing.
Yeah, the rope is here, although you can't tell from that crappy picture. Oh, and all the picture is going to be abstract. So there's going to be things like this, and that's going to represent this. Okay, it's going to be kind of abstract. Then I have another picture like this, like that, and that represents basically a block going down an inclined plane. Okay, it's kind of subtle. It's the abstract portion of class. Okay, then I want to have questions which are really kind of vague and obtuse, like, you know that thing with the trip? Yeah, what's the deal there? That's a hard question to answer. Just be prepared. Okay, so just a little final humor again. Okay, so when you draw this tension here, you put it right at the end here, right where it's at here, right at the edge. Okay. So that's the only one you need, but let's go through and put in the other ones as well. What else would there be on this wheel? Yeah, the weight would be acting at the center. There'd be one other force acting on this. Yeah, there'd have to be force from the support because that rod is holding everything. Why can't this be the only forces on it? It'd just be falling. Okay, so there has to be some force from the support like this. Now, is this moving up or down? No, so we're not going to worry too much about this coordinate system here, but what is it doing?
The block is moving down, the pulley is moving it all.
Okay, so what is it? But it is doing something. It's rotating faster and faster and faster in this way. So we need a sign convention for the torque. What's our sign convention for the torque? Yeah, always take the way the system rotates to be positive. So it's going like this, so we're going to say anything causing a rotation like that, a torque like that, is positive. Does that make sense? Okay. Now what? Yes, that's exactly what we do. So we come over here and we're going to say the net force equals MA. What's going to be the only component I'm going to worry about? Why? Because this is the only way it's moving. So we're going to say the net force in the y direction equals MAY. Okay? Which means we actually have to wait until basically summer comes before we can start this. If this felt like here, we can actually start it. It spells May instead. Is there no end to the humor in this class? I think not. Okay, okay, so what do we get for this?
We're doing it for the block now.
Yes, this guy.
Well, we're gonna get mg minus t.
Yes. And this equals MA, and I'm going to suppress the y here, and that's all we can have there. Okay? Yes.
So last night, I kind of, when we were doing this, I don't know if this was right or not, but I kind of cheated and used, looked up what I is.
Okay.
Was that what we were supposed to do? Or-
I have no, I read something about a pulley and something falling, and I thought, oh, good. Did it give you an eye? Or
It did not give me an eye, no.
Okay, so what would it be?
It's like 1/2.
MR squared would be a solid disk. Okay? Something like this, if it doesn't tell you what it is, if it's a solid disk, then you just do this 1/2 MR squared. I'll give you that in any of the exam questions.
Your cats will, right?
Yep, those crazy cats.
Can you put like a picture of your cat on class?
Yes, I will.
I'd appreciate that.
They look like this.
Just in the middle as like a little break.
They look like that.
You are not.
Uh-huh. Okay. Actually, two of them are mates.
Are you sure you didn't major in art and not physics?
You'd think, it's brilliant. It's a brilliant picture. Okay. Okay, so that's what we have there. Okay, what do we do with our friend here? Yeah, the net torque equals I alpha. What is alpha? Alpha is the, okay, what is it in terms of just words? It is the angular acceleration. It's telling you how fast this thing is speeding up this way. It's a change in the omega with respect to time. Okay, so there would be three torques here: the torque from the support, the weight, the torque, and the tension. So you have the torque from the weight, the torque from the support, plus the torque from the tension. Okay, now you don't need all three of these. How come? Now, these two are both going to be zero. Now tell me why these two here, these both are, they don't cancel, they're both zero individually. How come? Yes. They don't cause a rotation. Why don't they cause a rotation?
They act on the pivot point.
Yeah. Remember, the torque from any force is always R cross F. Where's your pivot here? Right at the center. This is the center. This is the pivot. So the R for the force from the support and the weight are both zero. These both have an R equals zero. So there's no pivot there. I mean, there's no moment arm. Okay? So what's the torque due to the tension? Where does R go? It goes from here. It goes from the pivot to where the force is applied. This is my R. You can see the magnitude of this is just going to be the radius. What angle does that R make with the tension? 90 degrees. So I work this out. What do we get? We get the torque from the tension. It's going to be what? R. Here's your force. I won't roll with that. This is R. This is your magnitude of the R. Your force, T, this is the magnitude of your force, okay? Times in 1, and so you'd have the sine of 90 degrees. Okay? And that's equal to your I times alpha. That make sense? What part?
Like, the R is,
This R here,
yeah.
so your little R goes from the pivot to where the force is applied. So the little r, your moment arm, in this case, is nothing but the radius of the wheel.
Okay. So if you were like, let's say there were any other, like if there was a tension on the other side of the
Okay. So if you had a guy like this,
yeah.
let's say this is T2, what would that be?
Or like negative.
It'd be negative because it's causing the opposite rotation. So this one would be minus capital R T2. Okay.
Let's say there was one coming off at a like. You
Smaller
see
distance?
what the pivot is? Like how you drew the line for the pivot from the, yeah. Like let's say there was something coming out of there, we would have to find the angle.
And so let's say somehow you had a force coming out like this.
Yeah.
Okay. I have no idea how you do that, but let's say you did. What would you do? Then you need, basically, then you need that R here, that R. Then you have to take this force here, break it up like this, and break it up like this. And the torque would be that this component here comes in this distance here. Okay, proceed.
Well,
I is
I is 1/2 sub 1/2 mr squared.
mr squared. What is alpha? How do we relate alpha to A? This is our A over R. What happens? This R cancels one of the R's here, and the remaining R then cancels out. So all the R's cancel. So this gets T equals 1/2 MA. So at this point here, you're done with the physics. Now you just have to be careful of the mathematics. Okay, where does this go? And this goes up into here. So you'd have, so I'm just going to write this exact equation here, but we're going to have the T and put in this right here. So this is mg minus 1/2 MA, right? Because this is my T, equals MA. What did you do next?
Solve for A by getting the A's on both sides.
Yeah, I took this over
We're on
here.
the same side.
I pull out the A. And I'll think about that prefactor, and we're done. So that will give us what would the tension be then? It'd be 1/2 mass. Now I need an A here. So I take this guy and I put this into here. So it'd be the mg over little m plus LMG. Does that make sense? Questions? Make sense? Yes.
So, L, right,
L.
what are the components? Because I feel like in the other ones, you have like PI and TF, and it's like.
Yep. This one I would not have you do anything with L in it, but I'll show you how to calculate it. Why would I not have you do anything with L in this problem? Normally, what does L always involve?
Momentum.
More? More? What about angular momentum? More? It's conserved. Would the angular momentum for the system be conserved? How come?
Because then, if the, depends on like, you probably do it with like braking and support, so that would like swing and fall.
No. When is angular momentum conserved?
Oh, the external torque view,
Are there external torques in the system?
yeah.
Yes, it's from gravity. Here's your pivot. Here's your pivot. Where would be the external torque from gravity? Where is it acting? It's acting in this guy here. This would be your R. This would be your external force, mg. And so there would be an RMG here. Okay? And so you'd actually have an external torque coming from gravity on that. Which makes sense, right? We can actually calculate this. Suppose I were to say calculate the angular momentum for this as an expression. What would it be? I wouldn't have you do that, but let's just do it. Suppose I say write an expression for L here. L for this system. I wouldn't have you do this, but let's say I did. Let's say my cats were having a really crappy day. I say do this. And they kind of do that maniacal cat laugh. Meow, 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 meow. Or they kick back their head.
Oh, wait, I think you can find angular acceleration using regular acceleration over R. Could you do that to get,
Uh-huh.
and then
We have two L expressions. What are they?
I alpha and then,
No. Angular momentum.
wait,
I
Oh
omega and
my gosh.
R cross P. Which one do we have here? We have both. You have two L's for the system here. We have L of the pulley plus L of falling mass. What would be the L of the pulley?
I omega one.
So this would be I the pulley times omega. Plus, what would you have for this guy? This would be R cross P, so this would be your magnitude of R cross P here. What would that be? How do you work out a magnitude of a cross product?
if I sign,
Okay, so you take the magnitude of R, magnitude of P, and the sine of theta. Look at this guy, what would you have? You can actually understand this problem, but I'm going to have you do this because there's some sort of research for that. So if you're to have this guy here, from here to there, this is R, right? This would be your P, your momentum, okay? So what we need here is that, here's your theta, like that. So tell me what this is going to be. You've seen this before.
oh, it translates to the R, or like becomes R.
Which are
The radius.
the radius. Right? This guy here, this R here is this magnitude of R sine of theta. Okay, so this would become I the pulley times omega plus R times the magnitude of P. What would be the magnitude of P? This would be MV. Okay. How'd you find V?
The acceleration.
You could. What else could you do? Okay, so if I were to give you this problem, there's two things that I'd ask. Either find the acceleration or to find the velocity of this, if it falls some distance h. That's connected with what? So say this falls some distance h like this. I want you to find the velocity here. What would you then do with this? Tell me why you would laugh and say, ask us a hard question. What is that problem though?
Oh, yeah.
It's the conservation of energy problem. Okay. Do you want to work out the conservation of energy part?
Sure. Sure.
So say you had something like this. This is initial ingress. This is going to fall some distance here like this, h. You define the velocity. Okay, proceed. You tell me what to do.
Looks like EI is gonna equal EF here.
How come?
Well, I mean, in addition to the fact that we already decided that's how we're gonna do it, there is no non-conservative work.
Okay, we're assuming that there's no friction at the dependent part here. Okay, so I'd say E initial equals E final. Energy is always made up of what two terms? Kinetic plus potential. Okay, What is our kinetic energy for the system initially?
Zero.
How come?
It's initially at rest.
It's initially at rest. What is our initial potential energy for the system? MGH or zero? Tell me why they're both the same. Let's start off with the MGH. Is you said MGH here? Okay, which is what I would have done as well. I'm just making an assumption here. What am I assuming is my zero?
The bottom picture.
Yeah, I'm taking this bottom here to be my H equals 0 line. So this is above that H equals 0 line, so that has gravitational potential energy. Suppose inside I said it's 0. Where am I taking that point to be?
The bottom or the start.
I'm taking it to be here. Okay, and now this fine. Okay, equals.
1/2 mv squared.
That's kinetic energy for the.
Whatever I don't know the name.
Okay, what did you say? 1/2 mv squared.
It's a translation.
What? Yeah, this is kinetic energy for the falling mass. You would call that translational kinetic energy. What else do we have here? Yeah, the pulley itself is rotating, so it has rotational kinetic energy, which is what? 1/2 I omega squared. Plus, what is your final potential energy? 0. So what do we have? We have MGH equals 1/2 mv squared plus 1/2. I is our 1/2 mr squared. Right, this is our I. What is omega? How do we write omega to be? Exactly what it is. This is our V over R quantity squared. What crazy thing happens with the R's? They cancel. So what am I left with? I'm left with 1/2 mv squared plus 1/4 mv squared. Okay. What would I do with that? Take out the v squared. Divide through by this mess here. Take the square root. That'd be. Yes.
Go over from the practice exam.
Yes, sir.
I think it was number 6 on part 2, or like the
6 on part 2.
or like whatever the part of it. It's like the one where it's like a sorry. There it is. It's like
Okay, so we have a whole bunch of things, and we want to rank things, and okay.
the first one, yeah, like with the tension and the 3 blocks
Yep.
being pulled by 1 string. Wouldn't the
So here's M1. Are they all different masses?
it doesn't mention anything. There's no friction, but it doesn't say anything about the mass.
Okay,
Just
so
asks which is the greatest tension, or like which,
I'll call this T3, I'll call this T2, and I'll call this T1.
or like rank the tension.
Okay, so rank the tensions. The thing is moving this way.
Is it 3, 2, 1?
Okay, so you're claiming it's this?
I claim that solely because it seems right, but also because I looked it up.
Okay, that's fine. Okay, this is the correct answer, but tell me why. So the question was, this is what, part 2? Number 6. Basically rank the tensions. So this is a claim. And it turns out to be correct. It is the correct answer. Prove it. What might be a good thing to start with? Yes. So let's look at M3 here.
For the sake of, can we like make them the same because it has T1 as the farthest?
So this is T1.
Yeah.
So,
Just to make it easier.
so is it then this guy?
Yeah.
Okay.
Yeah.
So then what's the answer here then? Is it that?
T1 is greater than T2, is greater than T3.
Try doing that in PowerPoint. Ha! Can't do that in PowerPoint either. And then the things that go all funny. I can make that. You can do jingle bells. Can't do that with PowerPoint. Okay, proceed. We're learning so much here. Some of it's even true. Okay, so what are all the forces on that?
There's a normal. Tension this way. There's a weight. That's it. Oh.
There's that right here. T2. Which way is this moving? It's moving this way. If it's moving that way, which of these forces have to be greater?
T1.
T1.
All right.
Hey, now tell me how this guy comes in. Let's look at M2. What are all the forces acting on our friend M2? Which tension? T2. What else? T3. If it's moving this way, T2 has to be greater than T3. That makes sense? Others? 2B. Part 1?
Yeah.
Okay, what is it?
It's the rod, the cable, and you cut the cable.
Oh, that's a cool question. Okay, so you have this guy here, and the rod, and this, and this is alpha. And you find the what?
The first part is to find the tension in the rod, and the second part is to find the angular momentum when you cut the
Find tension. Find angular momentum, or do you
Yeah, angular acceleration.
find alpha after cable is cut? And I told you that this is a rod. I of the rod is 1/3 L squared. This is L.
Most numbers.
Other number? Oh, just set up the expression for it. All right, let's start off, since we're running a little bit on time, let's do the latter part first. Okay, so first of all, let's draw the free body diagram for this. So if you draw the free body diagram for this, what is it? How would you, first of all, how would you even know to draw a free body diagram?
Why not?
Okay, that's not wrong. Okay, first of all, just do it, because it's not gonna hurt. But what would be the indication that you really want one? Yeah, you're having force words. Things like tension, acceleration, that screams free body diagram. Okay. So what are all the forces acting on that rod? Before it cuts, before the thing, before the cable is cut.
Oh, the tension in the cable.
Okay, so you'd have this would be the force from the wall. Why am I drawing it like that? Because I have no idea how it's going. So I'm drawing it like that, and if it turns out to be correct, you know, this is either right or wrong. I have no idea how it's going to go, so I'm drawing it like that. I'll work out the components and see what I get. Okay. What else? What else? The way acting where?
Right down the middle.
Right at the center. Okay, so this is what we have. Now, what's gonna happen? We're gonna cut the cable. Where's the pivot? Here's your pivot. And so after the cable is cut. After the cable is cut, right when it's cut, what does the free body diagram become? Yeah, your free body diagram is in this. It's that, right at that moment. I want you to find alpha. What would you then do for alpha? I mean, not this alpha. The alpha, this alpha, not this alpha. And this is going to be your net torque equals I alpha. What is the torque if this is my pivot? If this is L, what then is my torque from this diagram? What? So only the torque coming from this guy. Torque is always what? R cross F. So what is my R? It goes from here to there. So what is this distance? 1/2 L. What is my F? mg. And then what is the angle between the R and the F? 90, so the sine 90 is 1. This has to equal 1/3 ml squared. Okay, times alpha. What happens? Masses go out.
One of the L's.
One of the L's go out. Now take over the 3, so this gives me 3/2 G equals L alpha. So my alpha is 3G over 2L. At that point, that's going to change.
Wait, so that's just solving, or could we solve for the, I think the first part was solve for the tension in the cable.
Yeah, we did this part first because we were running out of time. This works faster. Tomorrow we'll do the tension part tomorrow.
All right.
Okay. So look through your first 3 tests and through the final. See if you have any questions, and I'll gladly answer them tomorrow. Okay. Feel free to come by if you have any questions or ask me for a Zoom meeting or something. I'll gladly do that. Make sense?
Dr. Locks,
Yeah, yes, Ellie.
is it possible to meet tomorrow before class or anytime that works with you? Because I have tomorrow at 12, I have you until 12, I have your class, and I have a organic chemistry class until 1.
I can meet you. I can. That'll work, but I can't do it right after class. If you want, I can do. I mean, before.
Oh, I can't do it right after class. I have an organic chem.
No,
lecture.
I misspoke. I can't do it before class because I have a. I'm actually in a class myself, so I can't do that.
Okay.
How about? When are you free?
I'm free after 1 p.m. or 1:20 technically.
Okay, that'll work tomorrow. How about? Can we do that?
Yeah, that would be great. Thank you so
Okay,
much.
so yeah, so tomorrow. Now you're gonna come in person, or do you want me to send you a Zoom?
In person would be great.
Okay, that's fine. Okay, so why don't you come by like, you're gonna come by at 1 or 1:20, or I don't care.
I have lectures from 12 till 1.
Okay,
Yeah, 1:20-ish because I have to drive there.
okay, that's fine. So why don't you come by?
Right.
Okay,
Great, got it. Thank you so much.
you're welcome.
Have a good day. Bye-bye.
Bye-bye.
Dr. Wells?
Yes.